I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today, we are going to discuss different topics related to laser emission. So we know that in day-to-day life, we have many applications of lasers. And this particular laser system, it has got very unique characteristics compared to normal light. So it is completely different from normal light source, and whatever characteristic it has made it have many applications. So today we are going to discuss what is the main phenomena required for laser emission and what are the different concepts related to a particular laser system. So if we see, we have different types of lasers being used in different areas of science, and each type of laser, it has its own power and it has its own advantage of application, and of course related to advantages there are some disadvantages also. So before knowing different types of lasers and their application, first we should try to get good clarity about what is involved in laser emission. So today, first in this video, we are going to discuss about basic concepts related to laser. Okay, we are going to first start with characteristic of laser. But before that, we should expand what is laser. We know acronym for laser. So what does laser stands for? As you can see, laser, it stands for light amplification by stimulated emission of radiation. So light amplification by stimulated emission of radiation. So as you can see here we have taken some new terms like light amplification, and second one is of course stimulated emission. So what exactly is this full abbreviation of laser? We are going to get idea once we discuss what are the basic concepts behind laser emission. So as you can see, full form of laser is light amplification by stimulated emission of radiation. So before going into what are the actual concepts or what are the different phenomena that lead us to laser emission, first we should see how laser light is different from normal light. So first we are going to discuss about characteristics of laser. So coming to different characteristics of laser. So here, when we compare our laser light with any conventional light source, what do you mean by conventional light source? We are talking about ordinary light source, and we know what are ordinary light source. Those are sunlight, tube light. Okay, so these are all normal light source, and this, if when you compare our laser light with normal light source, this particular sunlight or tube light, it has this phenomenon of spreading, and because of that spreading only, we are getting all such type of lightning. Suppose if we have a room, and in that room, if you want to illuminate with light, then we'll be making use of tube light or any bulb. And if you see this tube light or any bulb, it can spread throughout the room. So it will illuminate that room. But if we replace our normal sunlight, or if you replace your tube light or any bulb with laser source, then that particular laser source, it won't illuminate room. Why it won't illuminate room? Because it has its capacity of not spreading at all. So it has its own way of moving in single direction. So like that, so there are some characteristics which will make it completely different from normal light source. So when we consider those outstanding characteristics, as you can see, there are 4 specialized or unique features of laser light that makes it completely different from normal light source. And if you look at its characteristic, first one we are talking about directionality. Okay, then coming to second characteristic, we have monochromacity, and third one is highly intense. So laser light is highly intense. And fourth one, and of course most important one related to laser emission, is being coherent. So what are those 4 characteristics that will make it completely different from normal light source? First one is it has this characteristic of being directional. And then second one is being monochromatic, and of course it's a highly intense laser beam, and last one is it is a coherent laser beam. So now what we are going to do We are going to take each characteristic and we are going to see how it is going to be related to laser emission and how it is going to make it different from normal light source. So first we are going to discuss about directionality. So coming to directionality, now as you can see, what do you mean by being directional? So if you see here, if you call a particular light to be directional, it means that we are talking about its spreading. So here if you see laser light, it has this property of going in single direction. Its diffraction is very, very negligible. It has got very small diffraction. It will diffract, but the diffraction, it will be very, very small. And as you can see, all the light rays, laser, if you take laser beam, it is made up of many light rays, and all those light rays, they are going to travel in single direction. So that is the property of being directional. So as you can see, so compared to normal light source, this laser light, it will go only in single direction. And as I told, its diffraction property is very, very negligible, or you can also say that it can travel long distances without divergence. So its divergence rate is very small. So it won't diverge, it won't spread, and it will travel along single direction. And what do you mean by having no divergence? It means that its angular spreading will be less, and all the beams, wherever they are incident, they'll occupy small area. And if you want to express, if you want to see how the directionality of laser is different from normal light source, we are going to calculate it in terms of its divergence. And what is the formula for calculating divergence? The divergence, it is given as R1 minus R2 by T2 minus T1. And here as you can see, what we are going to do, we are going to take a screen, and then that screen, it is kept at two different distances from the laser source. And then what we are going to do on the screen, we are going to take radius of spreading of laser light. And what you will observe here is for two different distances from the laser screen, from the laser source onto the screen, radio of that particular laser spot, it is going to vary. And once we know that radius at two different distances, then we can calculate divergence of light using this formula. And when we have seen, it is observed that divergence for laser, it is very, very small, which is about 0.01 milliradian. Whereas if you compare it with normal light, it is 0.5 radian. So now coming to next property of laser, monochromacity. So if you see, what do you mean when you call a light to be monochromatic? So if you suppose if we compare our laser light with normal white light source, if you see white light, if you make it pass through a prism, then out of prism we are going to get beautiful colors. So we are going to get that spectra of colors, of GR colors. Why? Because that white light, it consists of different wavelengths. It has different colors of different wavelengths, and all those colors of different wavelengths, once they pass through the prism, their angle of refraction will vary, and because of difference in their angle of refraction, once the white light comes out of the prism, all the colors will get separated out. But if we make our laser light of one particular wavelength pass through the prism, then out of the prism we are going to get single line. We are going to get only single line. Why? Because this laser light, it is monochromatic. It has this property of having single wavelength. Now, what do you mean by having single wavelength? So as we are saying that it is monochromatic, it has got single wavelength. It means that line width of laser is extremely narrow. So what do you mean by having being monochromatic or having single wavelength? So it means that width of the line width of the laser, it is very, very small. And when we try to compare this line width with normal light source, we observe that in case of conventional light source, here in this case, its line width, it is in the order of 10 to the power of 6. Whereas if we take laser light, its order, it comes out to be 10 to the power of 5. So here you can observe that there is a change in the line width of laser compared to normal light source. And here, if you take a radiation which has got frequency of 10 to the power of 15 Hertz, then its line width, it comes out to be 1 Hertz. So here, that's why we come to conclusion that laser light is highly monochromatic, and there is a formula in order to get the degree of to how much extent that monochromatic property is there, we can find using this formula, which is given in terms of wavelength. Also, it is given in terms of frequency. Now, if you look at this degree of non-chromacity, it is given as d lambda by lambda. So, what is d lambda? It is the variation in the wavelength, and this can also be expressed in terms of frequency as d nu by nu, where d nu is variation in frequency. Now, going to next property of laser, highly intense. We know that in day-to-day life, we make use of laser light for soldering, cutting, okay, for smooth cutting, for soldering, and also for welding of dissimilar metals. So, it has this property of melting certain materials, and that property, it comes from its being highly intense. So, what do you mean by highly intense? It means that it has got very high power. So, power of laser is very, very high. And why it has this property of being highly intense? Because of its directionality. We know that if you take a laser beam, in that laser beam, we have different rays of light. All those light rays, they will occupy less area wherever they are incident. So, that's why, because here angular spreading is very less, divergence is very less. That's why what you will observe here is all the energy of those light rays, it gets concentrated in small region. And this concentration, it can be spatially or it can be spectrally, which makes its intensity enormous. It means that power is very, very large. So, if you see, look at this pulsed solid state laser, it is around 10 to the power of 9 watts. Okay, and where the diameter of laser beam is only 1 mm. And also we can calculate how many number of photons are coming from a laser per second per unit area using this formula. So what is N1? N1 is how many number of photons are being emitted per second per unit area, which is going to decide what is the intensity of laser beam. So when we say that laser is highly intense, it means that it has got more number of photons compared to normal light source. And in order to know how many photons are being emitted per unit area per second, then we can make use of this formula, which is given as P by H nu pi r square. Here, of course, P is our power of laser, and of course, H is our Planck's constant, and we know what is the value of Planck's constant, 6.6 into 10 power of minus 34 joule second. So, and what you will observe here is, if you take, of course, we were talking about this pulsed solid state laser. In case of pulsed solid state laser, which has got this power of 10 to the power of 9 watts, and if we consider diameter of the laser beam, which is around 1 mm, and if we take its radius as 0.5 into 10 power of minus 3 meters, then we'll observe that how many photons are emitted per unit area per second. It is around 10 to the power of 22 to 10 to the power of 34 photons per meter square second. So it means that large number of photons are being emitted compared to normal light source, and that makes our laser beam highly intense. Okay, and because of its high intensity and because of having very high power, as I told you, it is used for certain applications of welding, soldering, cutting, drilling, and even we can drill very hard materials also. Then going further to last property of laser, and of course, when we are talking about how many number of photons are emitted, there is one more formula using Planck's blackbody radiation. So using this formula also, we can find how many number of photons are emitted per unit area, and this is with respect to temperature. So we can make use of this particular formula, because as temperature increases, the number of photons emitted, their number will also change. And good example for this one is our black body. So if we take our black body, and we know that black body, it's a good emitter when we take it to high temperature. So with respect to temperature, radiation, intensity of radiation coming out of black body, it is going to change, and that particular emission of photons at a particular temperature, it is given by this particular formula. So when we compare, when we look at this particular calculation for a laser beam, we'll observe that number of photons will be very large. That will make it a highly intense beam. Then going to next one, coherence. So we know that even we were talking about this coherent property when we are taking our normal light source also. We have seen certain phenomena exhibited by light. So what are the phenomena exhibited by light? If you take interference, diffraction, there also we'll come across this property of being coherent. Then in what way laser light is different from normal light when we consider this property of being coherent? Now we have seen that if we take our normal light, suppose generally we'll do experiment in the lab where we'll make use of normal light source like sodium light, and using that sodium light we'll conduct a phenomenon of interference, and thus for interference to occur, in order to get interference pattern, we know that whichever light rays are superimposing on each other or which are overlapping with each other, they should be in coherent with each other, they should be in phase with each other, then only we'll have this property or we have this formation of fringes on the screen. Okay, and for that, scientist Young's, he has come out with one particular experiment, double slit experiment. So what he has done, according to him, if we take two different light sources, suppose I call those two different light sources to be S1 and S2, and these two are our normal light source or conventional light source. And if I take two different light sources and if I consider light waves coming from these two sources, suppose I have one light wave coming from S1, then I have another light wave coming from S2. And if I make these two light waves overlap, superimpose, and if I see on the screen, then I'll observe that there is no interference fringes formed on the screen. Why? Why is it so? Because these light waves, they are coming from two different light sources. And we know that when light waves come from two different light sources, they can never be in phase with each other. So, so this is the property. When we consider different light rays coming from different sources, they can never be in phase with each other. That's why we cannot get interference pattern on the screen. So for that, what Young's has done, he has come out this idea of dividing light into two parts by using division of wavefront. So what he has done, he has used a single monochromatic source and he made light or wavefront coming from that source divided into two parts by making it go through two slits. So as you can see from the main source, we have our wavefront, spherical wavefront coming out. And once this wavefront go through these two slits, then from these two slits, your light or wavefront, it gets divided into two parts. So here we have two wavefronts forming from each slit. Now these two slits, they'll act as virtual coherent sources. Okay, and as you can see, because these two wavefronts, which are visible as if they are coming from those two slits, because they are coming from the same light source, they will be in phase with each other, they will be coherent, and that's why on the screen we'll be able to see interference pattern. So what we are trying to say here is, if you take normal light source, in normal light source, if you take two different sources, then you cannot expect light waves to be in phase with each other. But that problem won't be there if I consider laser source. Okay. So if I take two different laser sources, suppose I am calling them as L1 and L2. But these two light sources, they should be of same type. What do we mean by same type? They should have same wavelength, frequency. Okay. So if you consider such two different light sources and if you take light wave coming from those two different laser light sources, then they can be in phase with each other and they can give rise to interference pattern. That is the difference between normal light being coherent and laser light being coherent. So we can expect light waves coming from two different light sources to be in phase with each other, which is not at all possible if we take our normal light source. Okay, and when we say these two light waves are in phase, when they maintain either zero or constant phase difference between them. So they have to maintain either zero or constant phase difference. When you say that they are maintaining a zero phase difference, when the positions are exactly matching, when crest of one wave exactly falls on crest of another wave, when trough of one wave exactly falls on trough of another wave. So when their positions are exactly matching, then we can say that they are in phase, they are maintaining phase difference of 0 degrees. And when we say that they are completely out of phase, when crest of one wave, it is falling on trough of another wave. So here in this case, we say that their phase difference is 180 degrees, they are completely out of phase. And there is one more concept of two waves maintaining constant phase difference. It means that if I take two light waves, throughout their propagation, they are going to maintain constant phase difference between them. Then if we consider all these three cases, suppose this is the first case where they are maintaining zero phase difference, second case when they are completely out of phase where their phase difference is 180 degrees, and third case where they are maintaining constant phase difference, then what we'll observe here is having 0 degrees phase difference or having constant phase difference will give rise to coherent light waves. So in order to be coherent, they should maintain either 0 phase difference or constant phase difference. And again, this coherence, if you consider, it is of two types. First one is temporal coherence and second one is spatial coherence. So what do you mean by temporal coherence? So here, generally temporal coherence will take it in terms of time, and whereas the spatial coherence will take it in terms of space. Suppose if I consider two different points in space, and if I call those two different points as P1 and P2, and if I make two light rays go through those 2 points, okay, so here actually what we'll do, we'll make those 2 rays going through these 2 points, okay, then what you will observe here is if they are maintaining either 0 or constant phase difference, then we call these 2 light waves to be spatially coherent. Whereas coming to temporal coherence, we'll select one single point in space and we are going to make light wave go through that particular point at 2 different times. Okay, we are going to take 2 different times, and at those 2 different times, by selecting one point in space, if we make light waves go through that point, and if they maintain 0 or constant phase difference at that particular point at 2 different times, then we call them to be temporally coherent. So these are the characteristics of laser. As we know that compared to normal light source, laser source, it has got some specific features like being directional, then being monochromatic, and then highly intense and coherent, which will make it completely different and which will make it have more applications compared to normal light source. Then moving further, now we are going to discuss certain phenomena that will help us in laser emission. Now coming to first phenomena, we are going to discuss about absorption. So phenomena of absorption, as you can see in this particular figure, we are talking about absorption in a system. So here I am going to take one term called as system. What do you mean by system? By system, I am calling I mean a matter system. So what do you mean by matter system? So it can be a solid, liquid, gas, or any other material which is made up of atoms or molecules, or it can be made up of some particles. So if you consider any matter system, and of course when we go inside the atom, we have our electrons. So we can talk all these phenomena in terms of atoms, or we can talk in terms of either electrons or some other particles. So if you take any type of matter system, and for simplicity's sake, in order to understand this phenomena of absorption, I have taken 2 active energy levels. Now, if you look at this figure, this lower energy state, let us call it as E1, and this higher energy state, let us call it as E2. So what I have done, I have taken 2 active energy levels in a particular matter system, and this lower energy state E1, and of course we have upper energy state E2. And if we take normal condition, what do you mean by normal condition? When we are not supplying any external energy to a particular system. So when we are not applying any energy, then obviously where will be our atoms or particles? Generally our atoms or electrons, they will be present in the ground state. We know that lifetime of ground state is very, very long. We can say it is unlimited. What do you mean by lifetime of ground state being unlimited? It means that if you don't supply any external energy, then electrons or atoms, they will try to remain in ground state forever. So that's why we say that lifetime of ground state is very large. So here, if you don't supply any energy, then you'll expect that atoms or electrons, they will remain in the ground state. Now, here we have taken one atom, and this atom, it is in the ground state. Now to such atom in the ground state, what I have done, I have supplied energy. And what type of energy I am supplying? As you can make out in the figure, I am making a photon. So I have taken photon. It means that I am supplying energy in the form of light. if you take high frequency radiation or highly intense beam, and if I make it fall on those electrons or atoms that are present in the ground state, then what you will observe here is, if I take this atom, okay, when this highly energetic photon falls on this atom in the ground state, then this photon, it is going to give its energy to atom, okay. And what should be the energy of photon? That energy of photon, it should be equal to difference between energies E2 and E1. So what should be that energy? Energy of the photon, it should be equal to H nu is equal to E2 minus E1. So when you take such photon, and when this photon is absorbed by atom in the ground state, then now atom, it will gain energy and it will get excited to higher state, which is nothing but E2. If we want our atom to go to E2, then we should supply energy, photon energy, which is equal to E2 minus E1. Then only this atom will go to E2. Otherwise, it will go to some other excited state. So here, as you can see in the second case, what happened after absorption? When atom in the ground state, it has absorbed this photon energy. Then as you can see, after absorption, we can find our electron or atom in the higher state. This process of excitation of atom or electron from lower state to higher state by supplying energy is nothing but absorption. So after absorption, where will be our atoms or electrons? They will be present in the higher excited state. Then moving to second phenomena. So coming to our second phenomena, as you can see, spontaneous emission. Now, in previous case, we were discussing about excitation of atoms from ground state to higher state. Now, here we are talking about de-excitation of atom from higher state to lower state. That is nothing but phenomena of emission. So, emission means where an excited atom will lose its energy and it will come down to ground state. And as we have seen that after absorption, where is our atom? Atom, it is in the excited state. Now, our question is, for how long this atom will hold that energy, or for how long this atom is going to stay in that higher excited state. So, as we know that every energy state, it will have its own lifetime. What do you mean by lifetime? Duration of time for which an atom stays in that particular energy state is nothing but lifetime. So, after lifetime, what happens to that atom which is present in that particular excited state? It is going to lose its energy spontaneously. So, what do you mean by spontaneously? On its own, it will lose energy and will come down to ground state. So, as you can see, when I have supplied energy atom, it has got excited from ground state to higher state. Now, this particular atom which is there in the excited state, after its lifetime, so as I told you, every energy state, it will have its lifetime. After lifetime, what happens to this atom? It is going to lose energy and it will get de-excited to ground state. And of course, we know that for excitation, we need to supply energy. And for de-excitation here, what will happen? Because it is coming from higher energy to lower energy state, then it is going to release energy. And how much energy it will release? Again, that energy, it is equal to energy of a photon, which is equal to difference between energies of E2 and E1. So, it means that when one atom comes down spontaneously without supplying any energy, per emission, I am going to get a photon. Suppose if 4 atoms are coming down because of spontaneous emission or after their lifetime from E2 to E1, then we have emission of 4 photons. So like this, if number of photons get multiplied because of spontaneous emission, we'll observe that what type of radiation we are going to get. We are going to get radiation where photons are completely out of phase and they have different wavelengths, and of course, they'll have incoherent radiation. So, what type of light we are going to take, which is not monochromatic and which is incoherent, okay, and it is a polychromatic light and it is also not highly intense. Why? Because as you can make out that per emission, we are getting only 1 photon. So, number of photons emitted per unit area per second will be less. So, that's the intensity of this light radiation will also be less. So here we cannot say that it is a laser light, because laser light characteristics are completely different from the characteristic of radiation which is emitted in this particular process. So now we are going to go for next very important phenomena which is directly related to laser emission, and that phenomena, it is called as stimulated emission. I think first When I started this video, I have abbreviated laser, and I told you that full form of laser is light amplification by stimulated emission of radiation. So in that we have this term stimulated emission. Now we are going to discuss what exactly is this phenomenon of stimulated emission. Now as you can make out here again, emission. Emission means where we have atom getting de-excited from higher state to lower state. Again, first, if you consider after absorption, when you are supplying energy to an electron or atom in the ground state, it will absorb that energy and it will go to higher state. So after absorption, where is our atom? Our atom, it is in the excited state. Now I want this atom to come down before its lifetime. I don't want that atom to stay in E2 for its lifetime, but I want to make it come down before its lifetime. So for that, what I'm doing, I'm supplying stimulus energy. So I have to supply some stimulus energy. So this is like pushing that excited atom down. I want this atom to lose its energy before its lifetime. So for that, what I'm going to do, I'm going to make use of one more photon, and this photon energy, it should be equal to E2 minus E1. So if I make highly energetic photon whose energy is equal to E2 minus E1, go and collide with this atom which is there in the excited state, then what we'll observe here is this particular photon, it will lose its energy and it will come down to ground state. So stimulated emission, stimulating means forcing. I'm forcing this atom to go to ground state before its lifetime. Anyway, it is going to come down. But after its lifetime, I don't want to wait till its lifetime. I want to make it come down before its lifetime. So that's why what I'm doing, I'm supplying stimulus energy. And when this photon goes and falls on this atom in the excited state, it will push that atom to come down. And when this atom comes down, or when it gets de-excited from higher state to lower state, how many photons are being emitted? There are 2 photons. And why we are going to get 2 photons? One photon, it is because of de-excitation from higher state to lower state, and second photon is our incident photon, which is acting as stimulus photon, which is forcing this atom to come down from higher state to lower state. Okay, so per emission, how many photons are being emitted? 2 photons are emitted. If 4 atoms come down, then how many photons total? 4 into 2, 8 photons are being emitted. It means that number of photons emitted per unit area per second will be more. It means that we are talking about highly intense radiation. And what you will observe here is whatever photons are being emitted, when they travel, okay, they will maintain either zero or constant phase difference. It means that they are in phase with each other and they will travel in single direction and they will have same wavelength. Their line width will be very, very small. So single wavelength, they'll have single wavelength, their line width is very, very small. It means that ultimately what type of beam or radiation we are going to get because of this stimulated emission, we are going to have highly directional. Okay, because all those photons which are emitted, they'll move in single direction and they are monochromatic. What do you mean by monochromatic? Their line width will be very, very small, and because here number of photons emitted are also large in number, that's why we can say that it is highly intense beam. And last one is because they are maintaining constant phase difference, so they will be coherent. So ultimately, these are the characteristics of laser. So out of stimulated emission, we are going to get our laser. So what is the main phenomena that will give us laser? Stimulated emission. So today we have discussed about different characteristics of laser, where we have seen that how laser beam is completely different from normal light. And then after that we have taken 3 phenomena, very important phenomena. Of course, we are getting laser beam out of stimulated emission. But even we have very important role played by absorption and spontaneous emission also. When we move further, when we discuss about a particular laser system, we'll find that even this absorption and spontaneous emission phenomena are also very helpful for the emission of laser. So if we try to compare spontaneous and stimulated emission, I think this tabular column is going to help us. As you can see, in spontaneous emission, we don't have to supply any energy, no need of any stimulus energy in order to force atom to come down. So what is happening after lifetime, atom which is there in the excited state, it will come down on its own, releasing single photon. So it is going to emit single photon, and as we know that whatever photons are being emitted, their line width is very large. That's why it will give rise to polychromatic radiation. A number of photon emitted are very less, so that's why whatever radiation we are getting, it is less intense and they are less directional. Their angular spreading is more, and because these photons are out of phase with each other, we are going to get incoherent radiation. And who has just postulated this phenomenon of spontaneous emission? It was done by scientist Bohr. And if we take to any physics lab, what are the sources we can find that will give rise to spontaneous emission? We can have our mercury bulb or sodium vapor lamp. Now, completely opposite to it is our stimulated emission, where if you want to de-excite atom in the higher state to lower state, we need to supply external energy, and that energy is called as stimulus energy. And how many photons are emitted per emission? 2 photons, and all those photons, their line width is very small. That's why we'll get monochromatic radiation, highly intense, highly directional beam, which is nothing but our coherent radiation. And who has given this? Who has postulated this phenomenon of laser? It is given by scientist Einstein. And obviously, what are the examples for laser light? We can take any type of laser like ruby laser or helium neon laser, light coming from all those laser sources. Obviously, they have this characteristic of being coherent, highly directional, monochromatic, and highly intense. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.